Aging is often treated like a slow, unavoidable decline. But what if a simple change to your morning routine could influence how your body repairs itself, how it burns fat, and even how it protects against serious disease? Imagine a daily habit that costs less than $1, yet activates biological systems in your body that most people over 60 assume are already lost forever. Systems responsible for regeneration, energy production, and even cellular defense. Now think about this carefully. What if one small addition to your morning coffee could influence 3 major processes at the same time? The regeneration of stem cells, the control of abnormal cell growth, and the reduction of dangerous fat stored around your organs? Most people are never told about this connection, not because it is hidden, but because the science has only recently become clear enough to fully understand. The truth is, aging after 60 is not just one process. It is a combination of multiple biological shifts happening at the same time, reinforcing each other in ways most people never realize. And once you understand these changes, you begin to see why energy drops, why recovery slows, and why the risk of chronic disease rises so sharply with age. Inside the human body, 3 major systems begin to weaken together. The first is the energy system inside your cells. These tiny structures, known as mitochondria, are responsible for producing nearly all the energy your body uses. In younger years, they operate at full capacity, allowing muscles to recover quickly, the brain to stay sharp, and physical energy to remain stable throughout the day. But over time, their number and efficiency decline significantly. By later adulthood, the body is often operating with nearly half the mitochondrial capacity it once had. This reduction alone explains why simple tasks begin to feel more tiring than before and why recovery after activity takes longer. The second major change involves your body's repair system. This system is driven by stem cells, which act like internal maintenance workers. Whenever tissue is damaged, whether in muscles, blood vessels, or internal organs, these cells are responsible for replacing damaged tissue with healthy new cells. In youth, they are abundant and highly active, but with age, their numbers drop dramatically. Research shows that their circulation in the bloodstream can fall by more than half as people grow older. This means the body's ability to repair itself weakens significantly over time. Wounds heal more slowly, internal tissues regenerate less efficiently, and small damages that once would have been repaired quickly can now accumulate. The third major shift involves how the body processes energy from food. In younger years, the body efficiently switches between burning glucose and burning fat depending on need. But as people age, this flexibility decreases. Cells become more dependent on glucose, and the ability to use stored fat as fuel declines. This change is not just about weight gain. It also affects how cells function at a deeper level. Certain abnormal cells, including those that can become cancerous, rely heavily on glucose to grow and multiply. When the body becomes overly dependent on glucose, it unintentionally creates an environment that supports this type of cellular behavior. What makes these 3 systems so important is that they do not fail independently. They are deeply connected. When energy production drops inside cells, it increases oxidative stress, which damages DNA. That damage then places more pressure on already weakened stem cells. At the same time, reduced metabolic flexibility makes the internal environment more dependent on glucose, which further stresses the system. One problem feeds the next, creating a cycle that becomes more pronounced with age. For many years, this combination was seen as unavoidable. Aging was considered a slow but fixed decline in function that could be slightly improved through general lifestyle changes, but not truly influenced at a cellular level. However, recent research in metabolic science has challenged that view. Scientists are now identifying specific dietary components that can influence all 3 of these systems at once. One of the most interesting discoveries involves a specific type of fat that behaves very differently from the fats most people consume daily. Unlike long-chain fats found in typical foods, this fat is processed rapidly by the body and converted into an alternative energy source that changes how cells function. Instead of being stored, it is quickly used to produce molecules known as ketones, which act as a clean and efficient fuel for the body and brain. These ketones do more than provide energy. They also send signals at the cellular level that influence fat metabolism, mitochondrial function, and even stem cell stability. This means they are not just fuel, but also biological messengers that affect how the body behaves at a deeper level. What makes this especially interesting is that this effect can be triggered through a simple addition to something millions of people already drink every morning. Coffee, when combined with this specific fat, becomes more than a stimulant. It becomes a delivery system for metabolic change. At this point, researchers began asking an important question. Could this combination influence not just energy levels or weight, but also the deeper systems responsible for aging itself? The answer began to emerge through multiple clinical studies that looked at fat metabolism, ketone production, and cellular function in older adults. And what they found opened the door to a completely different way of thinking about nutrition. After 60, in the next part, we will go deeper into how this specific fat works inside the body, why its structure matters so much, and how it begins to shift your metabolism from energy storage toward energy burning in a very short period of time. To understand why this approach is gaining so much attention in metabolic research, we need to look more closely at the specific type of fat involved and how it behaves once it enters the body. Not all fats are processed in the same way, and this difference is the key to everything that follows. The focus here is on a group of fats known as medium-chain triglycerides. Unlike the long-chain fats found in most everyday foods, these are structurally shorter, which completely changes how the body handles them. Long-chain fats require a complex digestion process. They are broken down, packaged, transported through the lymphatic system, and often stored before being used. This process takes time, and in many cases, leads to fat being stored in the body rather than burned for energy. Medium-chain triglycerides behave very differently. Because of their shorter structure, they bypass much of the digestive process. Instead of being stored, they are transported directly to the liver, where they are rapidly converted into a usable energy source known as ketones. This shift happens quickly and efficiently, changing the body's fuel supply in a way that is not dependent on carbohydrate intake or fasting alone. These ketones, especially a type called beta-hydroxybutyrate, are where the real biological effects begin to appear. They are not just an alternative fuel source. They function as signaling molecules that influence how cells operate. When ketone levels rise, the body begins to shift away from glucose dependency and moves toward a more stable and efficient energy state. This shift has several important consequences. First, it changes how fat is used. Instead of being stored, fat is more readily broken down and converted into energy. This is particularly important for visceral fat, the type stored around internal organs. Visceral fat is not just passive storage. It actively releases inflammatory signals that affect metabolism, insulin sensitivity, and long-term disease risk. Reducing this type of fat has been strongly associated with improved health outcomes in multiple clinical studies. When medium-chain triglycerides are introduced consistently, research has shown measurable changes in fat metabolism. Participants in controlled trials consuming these fats experienced greater reductions in body weight compared to those consuming other types of fats with the same caloric value. More importantly, the reduction was not just general weight loss, but a specific decrease in visceral fat, which is metabolically more dangerous. At the cellular level, this happens because ketones activate specific genetic pathways involved in fat oxidation. These pathways increase the body's ability to break down stored fat for energy. In simple terms, the body receives a signal that encourages it to use fat more efficiently as fuel, rather than storing it for later use. But fat metabolism is only one part of the story. The more significant effects appear in how these ketones interact with mitochondria, the energy-producing structures inside every cell. As previously discussed, mitochondrial function declines with age. Cells gradually lose efficiency. producing less energy and generating more oxidative stress. What research has shown is that ketones can stimulate a process known as mitochondrial biogenesis. This is the creation of new mitochondria within cells. In other words, instead of simply slowing decline, the body is capable of rebuilding part of its energy system under the right conditions. In clinical studies, individuals who supplemented with medium-chain triglycerides showed increased markers associated with mitochondrial activity. In practical terms, this means their cells were not only producing energy more efficiently, but were also increasing their capacity to produce energy in the first place. This is a significant shift in how aging is traditionally understood. Another important effect occurs in muscle tissue. As people age, muscle loss becomes a major concern, not just for strength and mobility, but also for metabolic health. Muscle tissue plays a central role in regulating blood sugar and overall energy balance. Loss of muscle mass is strongly associated with increased frailty and higher risk of chronic disease. Ketones appear to help preserve muscle in two important ways. First, they reduce the need for the body to break down muscle tissue for energy during periods of lower food intake. Second, they activate signaling pathways involved in muscle protein synthesis. This means the body is more likely to maintain or even build muscle tissue under the right conditions, even when in a mild calorie deficit. Clinical trials comparing individuals on identical diets have shown that those supplementing with medium-chain triglycerides not only lost fat more efficiently, but also preserved or gained lean muscle mass, while control groups often lost muscle along with fat. This difference is critical, especially in older populations where muscle preservation is directly linked to longevity and independence. As these metabolic changes continue, another layer begins to emerge involving cellular protection and stem cell behavior. Stem cells, as previously mentioned, are essential for tissue repair and regeneration. However, they are highly sensitive to metabolic conditions in the body. When ketone levels rise, they influence signaling pathways that help maintain stem cells in a more stable and protected state. This reduces the rate at which they become depleted or damaged over time. In practical terms, this means the body retains a greater capacity for repair as it ages, which has wide-ranging implications for tissue health and recovery. At the same time, elevated ketone levels also lower dependence on glucose as a primary energy source. This is important because many abnormal cells, including cancer cells, rely heavily on glucose for rapid growth. By shifting the body's energy environment, ketones help create conditions that are less favorable for this type of metabolic activity, while still supporting healthy cells that can efficiently use alternative fuels. This combination of effects is what makes this intervention so significant. It does not target one system in isolation. Instead, it influences multiple interconnected systems at the same time, including energy production, fat metabolism, muscle preservation, and cellular maintenance. However, none of these effects occur automatically. The dosage, timing, and form of consumption all play a role in determining how effectively the body responds. This is why researchers emphasize not just the ingredient itself, but the method of use. In the next section, we will explore how these clinical studies were conducted, what exact results were observed in controlled environments, and how researchers measured changes in fat loss, energy production, and metabolic health with precise data. To understand whether these effects are truly measurable in humans and not just theoretical biology, researchers have turned to controlled clinical trials that examine how medium-chain triglycerides influence metabolism over time. These studies are important because they remove guesswork and focus only on measurable biological changes under strict conditions. One of the most referenced trials in this area involved adult participants who were monitored over several weeks while consuming a fixed amount of medium-chain triglycerides daily. The goal was to compare their results against a control group consuming the same number of calories from a different fat source. This is important because it isolates the type of fat as the only variable, removing confusion about calorie differences or overall diet changes. What researchers observed was a clear shift in body composition. Both groups consumed similar calories, but the group receiving medium-chain triglycerides showed a significantly greater reduction in total body weight. More importantly, the quality of that weight loss was different. Instead of losing weight evenly across all fat stores, this group showed a more targeted reduction in visceral fat, the type stored deep around internal organs. This matters because visceral fat is not just a passive energy reserve. It is metabolically active tissue that releases inflammatory compounds into the bloodstream. These compounds are linked to insulin resistance, cardiovascular disease, and increased long-term health risks. A reduction in this specific fat type has been associated with improved metabolic health markers in multiple independent studies. Researchers also used metabolic testing to measure how the body was using energy at a cellular level. They found that participants consuming medium-chain triglycerides had a higher rate of fat oxidation, meaning their bodies were actively burning more fat for energy throughout the day. This was not a small change. It was a measurable shift in how the body selected its fuel source. At the same time, blood markers showed increased ketone production, confirming that the body was entering a mild state of nutritional ketosis even without strict dietary restriction. This is important because it shows that metabolic changes can occur without extreme dieting, fasting, or carbohydrate elimination. Beyond fat loss, another key area of interest in these studies was energy production inside cells. As people age, mitochondrial function declines, which directly impacts energy levels, endurance, and recovery. Researchers began looking at whether medium-chain triglycerides could influence mitochondrial activity in a meaningful way. What they found was a measurable increase in markers associated with mitochondrial biogenesis. This is the process by which cells create new mitochondria, effectively increasing their energy-producing capacity. In participants receiving supplementation, there was evidence of increased expression of genes involved in this process, suggesting that the body was actively improving its internal energy infrastructure rather than simply maintaining it. This finding is significant because it challenges the long-held assumption that mitochondrial decline is entirely fixed with age. Instead, it suggests that under certain metabolic conditions, cells can be encouraged to rebuild part of their energy system. Alongside these changes, researchers also observed improvements in physical performance. Participants demonstrated higher endurance capacity and improved energy output during controlled exercise testing. This aligns with the idea that more efficient mitochondria translate directly into better physical function. Another important aspect of these studies involved muscle preservation. As previously mentioned, aging is often associated with gradual muscle loss, which contributes to reduced strength and increased frailty. In controlled trials, individuals consuming medium-chain triglycerides while following a calorie-controlled diet were able to preserve more lean muscle mass compared to those on standard fat intake. In some cases, participants even gained small amounts of lean tissue while losing fat, a combination that is typically difficult to achieve in older adults. This suggests that the metabolic environment created by ketone production may help shift the body away from muscle breakdown and toward more efficient protein utilization. Researchers believe this effect is linked to how ketones influence cellular signaling pathways involved in muscle maintenance. When ketone levels rise, the body appears less likely to break down muscle tissue for energy, especially during periods of lower calorie intake. Instead, it preserves muscle while continuing to use stored fat as fuel. At the same time, ketones may also interact with pathways involved in protein synthesis, allowing muscle tissue to be maintained or slightly increased when combined with adequate nutrition and physical activity. This dual effect is what makes the findings particularly interesting in older populations. Another area of focus in the research is how these metabolic changes affect long-term disease risk. While the studies are not designed to claim direct disease prevention, they do measure biomarkers associated with health outcomes. In participants using medium-chain triglycerides, improvements were seen in several of these markers, including reduced triglyceride levels and improved insulin sensitivity. These changes are important because they are often used as indirect indicators of metabolic health. Lower triglycerides and improved insulin response are both associated with reduced risk of metabolic disorders over time. As these findings began to accumulate, researchers started connecting the effects of ketone metabolism to broader biological systems, including cellular repair mechanisms and stem cell regulation. Early evidence suggests that ketone availability may help stabilize certain cellular environments that support long-term tissue maintenance, although this area is still under active investigation. What is clear from the data so far is that the effects of medium-chain triglycerides are not isolated to one system. Instead, they appear to influence multiple interconnected pathways at the same time, including fat metabolism, energy production, muscle maintenance, and cellular signaling. However, researchers also emphasize that these effects depend heavily on how the fat is consumed. The dosage, timing, and method of preparation can significantly influence how well the body responds. Without proper use, many of the metabolic benefits may be reduced or inconsistent. This is why protocols used in clinical settings are very specific about how medium-chain triglycerides are introduced into the diet. Small differences in timing or preparation can change how efficiently ketones are produced and how effectively the body transitions into this metabolic state. In the next section, we will move from clinical research into practical application. This includes the exact protocol used in studies, how it is implemented in daily life, and the specific steps required to activate these metabolic pathways consistently without causing digestive issues or reducing effectiveness. When researchers move from controlled trials into real-world application, the focus shifts from what works in theory to what can be consistently replicated in daily life. This is where most nutritional interventions fail. Not because the science is wrong, but because the protocol is not followed correctly or is too vague to maintain long-term. In the case of medium-chain triglycerides, the clinical benefits depend heavily on three factors: the type of oil used, the dose, and the timing of consumption. When these are aligned correctly, the metabolic effects seen in studies can be reproduced with surprising consistency. When they are not, the results become inconsistent or minimal. The first and most important factor is the type of fat itself. Medium-chain triglycerides are not all identical, even though they are often labeled under the same category. They consist of different chain lengths, and each behaves differently in the body. Among these, one form stands out for its efficiency in producing ketones: caprylic acid, also known as C8. C8 is rapidly converted into ketones in the liver, making it the most efficient form for triggering the metabolic shift discussed in research. Other forms, such as C10, convert more slowly, and C12 behaves more like a traditional long-chain fat, offering far less of the ketone-related benefits. This distinction is critical because many commercially available products contain mixed or lower quality forms that dilute the intended effect. The second factor is dosage. In clinical settings, researchers typically start with a low dose and gradually increase it to allow the body to adapt. This is not only for effectiveness, but also for digestive tolerance. Medium-chain triglycerides are processed primarily in the liver, and when introduced too quickly or in large amounts, they can cause temporary digestive discomfort. Most protocols begin with a small amount, such as a teaspoon, and gradually increase over several days or weeks until reaching a level that produces consistent ketone elevation without side effects. In research studies, daily intake often falls within a moderate range that balances effectiveness with tolerability. The third and perhaps most overlooked factor is timing. When medium-chain triglycerides are consumed, significantly affects how the body responds. The strongest metabolic effects occur when they are taken in a fasted state, typically in the morning after an overnight fasting period. During this time, insulin levels are naturally low, glycogen stores are partially depleted, and the body is already shifting toward fat metabolism. Introducing medium-chain triglycerides at this point amplifies that shift, increasing ketone production and accelerating fat oxidation. If consumed alongside high-carbohydrate meals, however, the effect is significantly reduced because insulin suppresses ketone production. This is why many protocols emphasize taking medium-chain triglycerides in coffee shortly after waking. Coffee itself plays a complementary role due to its caffeine content, which independently increases fat oxidation and stimulates the release of stored fatty acids from fat cells. When combined, caffeine and medium chain triglycerides create a coordinated metabolic effect. Caffeine mobilizes stored fat, while ketones provide a direct and efficient fuel source to burn that released fat. Without ketones, the released fat may be restored. Without fat mobilization, ketones alone have less substrate to act upon. Together, they create a more complete metabolic cycle. Researchers have observed that this combination can significantly increase overall fat oxidation compared to either compound used alone. The interaction is not simply additive, but synergistic, meaning the combined effect is greater than the sum of each part individually. Beyond fat metabolism, timing also influences how the body engages mitochondrial and cellular repair pathways. In the morning fasted state, the body is more responsive to metabolic signals that encourage energy production and fat utilization. This is also when ketone levels have the greatest impact on cellular signaling related to energy efficiency and stress resistance. Another important aspect of the protocol is consistency. Unlike short-term interventions that produce rapid but temporary results, metabolic adaptation requires repeated exposure over time. The body gradually shifts its enzyme activity, gene expression, and fuel preference based on repeated signals. This means that benefits accumulate over weeks rather than days. In clinical observations, noticeable changes in energy levels often appear within the first 2 weeks. These include improved mental clarity, reduced morning fatigue, and decreased hunger between meals. These early changes are primarily driven by the brain's response to ketones, which serve as a highly efficient fuel for neural tissue. More structural changes, such as fat reduction and improvements in body composition, typically become visible after several weeks of consistent use. These changes reflect deeper metabolic adaptations, including increased fat oxidation, improved mitochondrial function, and more stable energy regulation throughout the day. Over longer periods, typically 2 to 3 months, researchers observe broader improvements in metabolic health markers. These can include reductions in triglycerides, improved insulin sensitivity, and more stable energy output during physical activity. These changes reflect systemic adaptation rather than short-term fluctuation. It is also important to recognize that this protocol does not operate in isolation. Its effects are significantly influenced by overall lifestyle factors, including diet composition, physical activity, and sleep quality. For example, resistance training enhances the muscle-preserving effects of ketones by providing a mechanical signal for growth and repair. Without this stimulus, some of the muscle-related benefits may be reduced. Similarly, excessive caloric intake can blunt fat loss effects even if ketone production is elevated. The metabolic system is responsive, but it still operates within the broader context of energy balance and nutrient availability. This is why researchers often recommend pairing this approach with moderate dietary control rather than extreme restriction. A slight calorie deficit combined with improved metabolic efficiency tends to produce more sustainable results than aggressive dieting alone. As these practical insights are applied, the next question becomes what real-world results look like over time and how the body adapts across different stages of implementation. This includes early changes in energy and appetite, midterm changes in fat composition, and longer-term changes in metabolic health and physical performance. In the next section, we will examine these outcomes in detail, including how individuals typically respond during the first weeks versus after sustained use, and what measurable changes researchers have documented across different timeframes.